It's good to be here. So I'm going to switch gears a little bit from what we started with this morning. Have a history and experience studying variously snow and glacier ice fracture. And in recent years, I've been working a lot on ice shelves in Antarctica and modeling ice shelves and thinking about how floating glacier ice fractures. So that's going to be the main focus of what I'm going to talk about here. And I wasn't sure how much glaciology background this audience would have, so I'm going to start with just a little bit of a kind of background, set the stage a little bit for why ice shelves are important, what's going on in Antarctica that makes them worth looking at. So here's a picture of Antarctica with the ice shelves shaded in, I don't know what you call that color, some kind of rose. Most of the ice on the continent of Antarctica drains to the ocean through these floating ice shelves. So most of the ice gets delivered to the ocean via ice shelves. And ice shelves are important because they provide a measure of buttressing to the ice sheet. So they're sort of like corks in a bottle. Most ice shelves are contained within embayments of some sort that provide some resistance to flow, and that resistance is felt by the ice sheet. And without an ice shelf there, the ice would be delivered to the ocean much faster. So the ice shelves are kind of plugging the ice sheet around the perimeter to some degree. One reason this is particularly important, especially in a place like West Antarctica here, this is considered the West Antarctic ice sheet, East Antarctica over here, is much of the bedrock of the ice sheet is below sea level, well below sea level. So there's a lot of sea level potential if this ice sheet were to collapse, and there's reason to believe that an ice sheet sitting on bedrock below sea level is potentially unstable. And many of the changes that we're seeing around the perimeter of the ice sheets, this goes for Greenland as well, but especially for Antarctica, the changes that we're observing are most concentrated around the perimeter of the ice sheet. So this is a picture from a study that looked at laser altimeter data, looking at elevation change over time around the perimeter of the ice sheet. Red color is surface lowering, and you see the most kind of red colors around the perimeter of the ice sheet near the coast, and especially here in West Antarctica, a lot of change going on in this region. And the reason that things are happening so rapidly on this part of the continent is that this is where we're getting the most melting of ice shelves from below by the ocean. So we get warm water, comes up onto the continental shelf and floods the cavities beneath these ice shelves, melts them from below. As the ice shelves are thinner, they provide less buttressing to the ice behind, allowing increased discharge of ice then into the ocean. We're seeing less melting, but some, in places like the Antarctic Peninsula, the two big Ross and Ronny ice shelves have less going on in terms of melting and dynamic change than here in West Antarctica, where we're getting very high rates of melting at the bottom of these ice shelves. So if we think about what's going on for what we call a marine ice sheet, this is an ice sheet that is grounded on bedrock below sea level. We can, if we think about an ice sheet in a sort of one-dimension, in a one-dimensional context, we can describe the flux of ice at the grounding line, which is where the ice first comes afloat. So an ice shelf would be right here. This is the ice sheet grounded on some sort of bedrock or till. We can characterize, we could derive, and maybe I should have shown the full equation here, given that this is a sort of mathematical workshop, but this is the way I usually present this, that we can characterize the flux at the grounding line as a function of the ice thickness to some very large power. So the amount of ice fluxing across the grounding line in steady state is a function of the ice thickness to something like the fifth power. So if we have an ice sheet in steady state, sitting on bedrock below sea level, and if that bedrock slopes downward toward the interior of the continent, which is common because the ice is heavy and it's depressing the lithosphere, we have a potentially unstable situation, because we have, if the ice is in steady state here, we've got the amount of ice delivered to the grounding line, which is a function of essentially the amount of snowfall accumulated over the ice sheet through time being carried toward the grounding line. But the flux at the grounding line there is a function of the ice thickness to some very large power. If we get water start coming in and melting the ice shelf from below, that will cause the former grounding line to start to float, and the grounding line to migrate down to deeper bedrock. And now you've got a situation where you've got slightly thicker ice at the grounding line, and because of that power law relationship, big increase in flux there at the grounding line. But the flux delivered to the grounding line hasn't changed. That's a sort of integral of the ice accumulation through time. So you've set up a sort of dynamic imbalance here that will be accommodated by dynamic thinning of the ice, and that will cause this grounding line to float off the bedrock and the grounding line to migrate to yet deeper bedrock. And so you've set up a feedback loop that would be, in theory, at least in one dimension here, unstoppable until you reached some change in slope of the bed. So you'd have some runaway instability, and this marine ice sheet instability has been discussed in the literature for many, many years, and is a cause of concern for the changes that we're seeing in the West Antarctic ice sheet. Many people believe that this sort of irreversible instability has already been set in motion.
Can I just ask a simple question? What's driving the flow? Because I would have thought it was being pushed, but clearly it isn't. So what's making it flow, that power to the 5? What's the force? What's the origin of the force?
It's just gravity. It's just gravity. It's driven by the surface slope of the ice sheet. It's a gravitational thin film flow.
Okay, yeah.
So this notion of changes in ice shelf buttressing associated with changes in the ice sheet was highlighted in the most recent IPCC report, and essentially they were saying that where we're seeing the biggest changes on the ice sheet, on the grounded ice sheet, are where we're also seeing the biggest changes in the ice shelves. And this is consistent with this idea that ice shelf buttressing is important to the ice sheet, and where we're seeing changes in ice shelf buttressing is naturally where we should then see changes in the dynamics of the ice sheet. But ice sheets are not one-dimensional. In the presence of ice shelf buttressing, you can actually stabilize a grounding line on a reverse sloping bed. So now looking at an ice sheet in plan view, top-down, these are modeling results demonstrating that you could stabilize a grounding line here in black on a section of reverse sloping bed between these two pink lines in the presence of strong lateral converging flow, which gives you a measure of ice shelf buttressing. So you could stabilize a marine ice sheet on that reverse sloping bed if you've got sufficient amount of ice shelf buttressing. And we could actually characterize in 2 dimensions the flux at the grounding line and add in a factor, a sort of buttressing ratio that accounts for this measure of ice shelf buttressing. And we see that the flux is sort of not as sensitive to the ice thickness at the grounding line as it is to buttressing, but there is a dependence there. And you could see that even in the absence of a thickness change, you could change ice shelf buttressing through something like fracturing and get a change in flux at your grounding line. So there are a number of mechanisms that could lead to reduced ice shelf buttressing, all of which in one way or another can relate to fracturing of the ice. So we can reduce the area of an ice shelf in contact with its embayment margins through processes like iceberg calving. We can weaken shear margins of an ice shelf. The shear margins are where the highest stresses are borne by an ice shelf. Or at the sort of ultimate limit, a collapse of an ice shelf removes buttressing entirely. So all of these relate in one way or another to fracture. So iceberg calving, there was recent media coverage of the loss of the large iceberg, A68 it was called, from the Larsen C ice shelf on the Antarctic Peninsula. This is a picture of that large rift through thickness fracture through sort of 200-300 meters of ice that cut out a about 6,000 square kilometer iceberg and released that to the ocean earlier this year. Here's a picture of the full iceberg when it was released. Now, in this case, there wasn't any, none of this ice at the front of the Larsen C ice shelf was providing any buttressing, so there probably isn't a huge change to the dynamics of the ice shelf here, but this is just one example of how removing a large chunk of ice could, through fracturing, could change your ice shelf buttressing. Shear margin weakening, so this is a picture of the floating tongue of Pine Island Glacier in West Antarctica. Ice is flowing top to bottom. Here we've got an example of both iceberg calving and the shear margin here being highly fractured, both of which, in this case, not much buttressing provided by this chunk of ice out here, but losing the ability to carry load in a shear margin like this would change the buttressing provided by this floating tongue. And then this classic sequence of ice shelf collapse. This is the Larsen B ice shelf on the Antarctic Peninsula. It collapsed in a matter of weeks in 2002 after a period of strong atmospheric warming, which caused all these melt ponds to appear on the surface of the ice shelf. And in a period of weeks in the early part of 2002, the ice shelf just disintegrated. And since that time, the glaciers that fed that ice shelf have continued to thin and accelerate over the course of at least a decade. So what we think was maybe happening in this instance, or the prevailing hypothesis, is that the surface melting led to surface ponding on the top of this ice shelf, and that gave rise to these sort of distributed disk loads on top of the floating ice that in principle would cause these ring fractures. And if these lakes drain, you'd get a sort of hydrostatic rebound, which would cause a reverse loading and fracturing at the bottom of the ice shelf. And if you drain, so if you were able to drain through hydrofracture one lake, it could lead to a chain reaction drainage of neighboring lakes through these fracture sequences that in principle could explain that sort of disintegration of the ice shelf. So that sort of just sets the stage a little bit for why we want to talk about ice shelves. They're thinning in many places in Antarctica. We know that the buttressing reduces as ice shelves thin and they shrink. The dynamics of the ice sheet, the changes are quite rapid, more rapid than previously thought. And we could, because of some of these processes, we could see considerably larger increases in sea level beyond what kind of the summary reports have estimated thus far. And all of these things relate potentially to fractures in the ice. And a lot of this is really not represented very well or at all in many of the models used to make projections of the future of the ice sheets. So then ice shelves are nice platforms for studying ice rheology. They've been used to study the sort of basic rheology of glacier ice for a long time. The main reason is because you've got ice that's sitting on essentially a frictionless bed. So compared to a grounded glacier, the dynamics are a lot simpler. So it's nice to look at floating ice for studying rheology. Early studies were used to sort of figure out what we think the power law creep exponent of ice should be. Nowadays, we kind of take it as a given that this creep exponent is 3, and then we can look at sort of spatial variations in ice property and find that ice is sort of softer in the shear margins where it's strongly shearing past embayment margins. And so what we commonly do now with these large-scale ice sheet models is we take satellite data and we assimilate using inverse methods to determine the spatial variation in ice properties, ice rheology. So that takes into account sort of what we commonly use as a form of what we call a flow law, or the constitutive relationship that relates the deviatoric stress to the strain rate through a non-linear viscosity term, a term that is also dependent on the strain rate. We sort of take for a given that n is 3 in glaciology. That's not entirely true, but we do it anyway. And this viscosity parameter is typically what we're inverting for on an ice shelf. We take that to be primarily dependent on ice temperature, but there are other factors that will certainly influence this sort of kind of bulk viscosity parameter. We use a adjoint-based inverse algorithm to determine parameters like B on an ice shelf, or alpha, which would be a friction coefficient or a basal shear stress on grounded ice, by minimizing a cost function that measures a misfit between a modeled velocity and a typically satellite observed velocity. Subject to our sort of governing equations, we model a glacier using Stokes flow relations with this nonlinear viscosity term. And typically for an ice shelf, this is what we want to invert for, is this viscosity parameter. Now we can actually generalize this to account for, in a continuum sense, to account for fractures by formulating an equivalence principle between our sort of homogenized, idealized model element and our actual sort of material that may have fractures in it. And if we postulate that we want the model to have the same strain as the actual material under a given load, we can sort of set up this sort of linear mapping that formulates an effective stress as a function of our sort of Cauchy stress divided by 1 minus a damage variable, where a damaged variable goes from 0 from sort of virgin material to 1 for fully fractured material. And then we can sort of generalize our flow law to account for damage. So as ice grows more damaged in a continuum sense, it will sort of deform more easily. So then if we're going to do this, we need, if we want to then invert for something like damage to get an idea from satellite data where ice is being deformed because it's fractured, then we need to actually have a sense of what the temperature of the ice is so that we can independently parameterize this viscosity parameter B, because now we've got sort of two unknowns, so we need to sort of partition those if we want to get a picture of what's going on from satellite data. So this is kind of one example of how I would go about that. On the Larsen B ice shelf, to calculate the temperature through the vertical column of the ice shelf, we need to know what's going on at the base. We can't measure the base, so we rely on another model to tell us, in this case, what the basal melt rate is from an ocean circulation model. Where the ocean is melting away at the bottom of the ice shelf, we actually have a removal of the warmest ice at the base of the ice shelf there. So actually, in a depth average sense, the resulting ice is colder. Whereas where we have accretion of marine ice at the base of the ice shelf, so freezing of seawater onto the base of the ice shelf, because of the latent heat release associated with that, in this case negative melt rate is accretion, here we get much warmer depth average ice temperature. So we can get sort of an idea of what the temperature of an ice shelf like this would be from this sort of idea, from at least in a steady state calculation. And for Larsen B, this is the part that collapsed here. We see that the ice was much warmer in the northern part of the ice shelf than in the southern part of the ice shelf that survived. So if we do that, then we can, if we sort of estimate what we think the ice temperature is, then we can invert for this damage parameter, this continuum parameter for representing fractures. So this was some results looking at the state of the Larsen B ice shelf before it collapsed in 2000, where red colors are damaged and blue colors are undamaged. There's a few things to note here. What we observed with this ice shelf is it was progressively retreating by calving over the course of almost a decade before it collapsed. And this little slice taken out here is an area that is the area that continued to calve icebergs up until the time it collapsed. So in a short window of time, we know that between these observations and when it collapsed, this area was sort of close to failing in terms of it was close to calving. So if we kind of look at the threshold values of damage in this area, we could postulate that we might be able to specify a damage-based calving law by looking at something like a threshold damage for calving. The other thing to notice is that the places where the ice is the most damaged or the most weakened is primarily in shear margins, where you've got ice flowing into the ice shelf and sort of strongly shearing either past other tributary glaciers that are moving at different speeds as they flow into the ice shelf, or shearing past sort of islands or grounded promontories. So we can do the same thing, another example of the same thing for the Larsen C ice shelf. This is the viscosity parameter, where you can see there are a number of fractures here that appear softer in a continuum sense, and we see that they turn out to be damaged. Things are a little smeared, and that has to do with the resolution of the observational data used as input in the model. And there are a number of areas where we clearly probably have the temperature of the ice shelf wrong. This is probably not damage. We actually have subsequently learned that there are a number of areas where the ice is actually a lot warmer than we thought. So this is not, really shouldn't be damaged. This should just be warmer ice to explain why it's deforming more easily. So I'm going to just briefly mention this interesting case from this iceberg that calved off Larsen C, because it does relate to fracture mechanics, and there's some really interesting fracture details going on here. So the ice is flowing out this direction into the ocean, and what I've drawn on here, there's these longitudinal stripes. These are what we call suture zones. These are bands of ice that separate boundaries between what were previously glaciers in neighboring valleys that flowed into the ice shelf and sort of merged together to become the ice shelf. And often what you have in these zones is, because you've got downstream of these promontories, you get strong upwelling of seawater, and you get accretion of ice at the base of the ice shelf. So you get often a substantial portion of your total column thickness is composed of this sort of warm, probably kind of mushy, probably kind of salty marine ice. In addition to having these former shear margins of neighboring glaciers come together. So it's quite a sort of heterogeneous bands of ice. And it turns out that these sort of bands of ice are very effective all around Antarctica at stabilizing fractures. So in this case, these fractures that I've drawn here, you get these fractures that first, these rifts through thickness, through hundreds of meters of ice. They first form as the ice clears this peninsula, this promontory, and you get a stress jump there that periodically causes these opening fractures. They shoot out, and they always pretty much stop at this boundary. So these older fractures here near the front of the ice shelf are over 100 years old. So for 100 years, these fractures, or longer, these fractures have been stabilized by this longitudinal band of kind of heterogeneous composition. And this one rift that popped through this band in 2014 is the one that resulted in this big iceberg. And we don't really understand what it was that allowed this one to pop through. But we did observe that as this rift propagated across the ice shelf, pretty much every time it encountered one of these longitudinal bands, it slowed down and paused for a while before it was able to overcome the resistance of that suture zone and keep going. So there's something very special about these suture zones for stabilizing fractures, and probably thus stabilizing ice shelves. And we don't understand all the details there yet, but it's quite an interesting story. So when this rift finally made it to the ice front, it sort of reached this last suture zone here and then strongly kinked and then sort of shot off a number of different branches before peeling off the final iceberg. But there is some fracture theory to suggest why a fracture would change direction when it either enters or exits a zone of strongly varying material properties. So I think there is something we can learn about the crack path taken by fractures like this. So it's kind of an interesting story. I'm not going to say much more about that. I'm going to come back to the Larsen B ice shelf here, and this little bit in the southern part of the ice shelf still remains, but it's been slowly, it's kind of slowly tearing itself apart since the rest of the ice shelf collapsed in 2002. So what we started collecting a time series of velocity observations, and we started performing these inversions to look at how the rheology of this ice shelf changed through time. The ice shelf here, in terms of velocity maps, you can see that the speeds are increasing through time, so that indicates that the ice is getting weaker. The viscosity, this viscosity parameter that we invert for, is getting sort of more and more red, so sort of more readily deformable ice through time from 2000, 2006 to 2010. We can parameterize a measure of buttressing, or what we sometimes call backstress, from these calculations as well. So more pink means there's more buttressing provided by the ice shelf. This has sort of decreased through time. Coincident with that, we're seeing acceleration of the glaciers and thinning of the glaciers that feed this ice shelf. So then what I did was I went and inverted for this damage parameter for these different years where we had good velocity coverage over the ice shelf to see how the damage changed through time. So that in 2000 here, for this portion of the ice shelf, this is when the full ice shelf was still in place. You had some kind of shear it was mainly some sort of shear margins that were weakening associated with these tributary glaciers coming down from the mountains. Then in 2006, the ice shelf had collapsed and retreated back to here. You had this lengthening of some shear margins, one rift here that eventually peeled off an iceberg here. 2010, further weakening, and 2015, kind of further gradual weakening of the ice in the ice shelf. So then the question is sort of what, how to put all these time series observations together into some sort of framework where we could actually model the evolution of this damage. So we commonly handle damage evolution through an advection equation because we're dealing with a viscous framework here. So we have the sort of total derivative of damage balanced by some source and potentially some sink terms. There have been a number of sort of kind of ad hoc source terms proposed for incrementing your damage variable in a framework like this. But what I wanted to do was think about changing the actual constitutive relationship rather than developing a some sort of source term in that sort of framework. So to talk about how I sort of got to that stage, I'm going to digress and talk a little bit about some smaller scale fracturing experiments and damage modeling that I did for snow. And this stuff actually follows quite nicely from the previous talk. So I spent my PhD studying fracture of snow related to slab avalanches. And I did a lot of fracture experiments looking at things like size effect, temperature effects, rate effects in mostly these kinds of like 3-point and 4-point bending measurements in a cold laboratory in Canada. And the nice thing about these kinds of experiments is I can work fairly close to the scale of what's actually happening in the field. So I'm looking at fractures on the scale of sort of a few, maybe 5 to 20 centimeters in the lab, whereas the fractures in the field that are related to avalanches, the tensile fractures anyway, that release a snow slab are on the scale of tens of centimeters to sort of meters. So I'm not too far from the scale that I'm interested in. So the types of experiments that I run in the lab give me these sort of common looking load displacement curves. These are not stable experiments. These are displacement controlled experiments. So I'm not measuring stable cracking in the softening regime here. This is just a rebound of the load cell essentially. But I can look at the size effect, or I can look at, another thing I look at is the comparison between notched and unnotched experiments at the same size, so the sort of zero brittleness method to fit a size effect law. And then I did some fully elastic damage modeling at the same scale of the experiments, and I used a local constitutive relation that's linear elastic up to some tensile strength, and then we specify an exponential softening curve after the peak strength is reached. And then, of course, the area under the curve is the fracture energy, which I could get from scaling the size effect experiments. So I can get all the parameters for an isotropic elastic damage model from the experiments. And I can run, in this case, model experiments for both notched and unnotched tests using the same set of numerical parameters derived from the experiments in both cases. And I can get actually a pretty decent agreement with the observation. So again, the sort of post-peak rebound, especially in the unnotched experiments here that fail at higher load, is kind of nonsense, but the pretty good agreement between the peak loads and the slopes of peak load between the notched and the unnotched experiments from one set of parameters. And the nice thing about a damage model in this context, and I think also in the context of the ice shelf stuff I'm doing, is you can get crack growth from a notch or a pre-existing crack, and you can get crack initiation from a smooth boundary within the same model framework. There's no need to assume or put in pre-cracks to get cracking, which is commonly done in many glacier contexts anyway. So one area where I think this elastic damage modeling is maybe quite appropriate is for thinking about these through thickness rifts that propagate across ice shelves. These are some field measurements near the tip of a rift in Antarctica from seismometers in triangles, and little pink squares represent seismic source locations that are interpreted to be the result of fracturing. So you see quite a distributed pattern of fracturing near the tip of this big rift, which you could interpret as being the result of sort of heterogeneity in the vicinity of a crack tip on a very, much different scale than you're maybe used to thinking about in terms of a lot of these acoustic measurements that have been looked at that are similar for concrete and other materials in the lab, but actually otherwise quite similar. So I think it would make sense to use, because we're seeing this as elastic behavior largely around a rift, I think it would make sense to use an elastic damage model here. But then, okay, so setting the stage, coming back to thinking about how to look at this damage evolution on Larsen B through time, what I did is I plotted the effective stress, so the scalar sort of second invariant of the deviatoric stress versus the strain rate for different years, and I colored the points here by the level of damage, blues from no damage up to yellows, damage approaching 1. And to me it looked similar to the way that I had previously modeled, or at least analogous to the way that I previously modeled these elastic fracture experiments. So it struck me that why not try specifying a similar constitutive relationship in the viscous case here. So saying that at a certain threshold stress we specify then a softening curve as a way of developing this damage evolution framework. So then it would be pretty straightforward to say that out of the data there's a threshold stress above which we do not see undamaged ice. So rather than allowing our constitutive relation to grow sort of without bound, we say we allow it to grow up to the threshold stress. And thereafter we specify this exponential envelope, which does manage to fit quite nicely against the data. So we would follow that down with increasing strain rate to some given level of damage. And then for any unloading or reloading, then we would be operating at this new level of damage. So these points, numbers here, represent the constitutive relationship as a curve at a given temperature for different levels of damage. So no damage, damage of 0.1, 0.2, 0.3. So then if I load it up to a damage of 0.5 and then I unload, I'm now following this new loading curve, and I would stay on that curve unless I exceeded this point, at which point I would again begin to soften and increase damage. So if I have this relationship for the constitutive relationship generalized for damage that expresses the strain rate and the stress, and I have this softening curve that I specify the form of, then I can actually put the two together and I can analytically solve for damage at a given level of strain rate. And I only need two extra parameters to do this, the threshold stress and this kappa, which tells me the initial post-peak softening slope of that exponential softening relationship. So then I have, rather than trying to formulate a source term for damage, I have an analytical solution for damage that is explicitly linked to the evolving stress balance of the ice. And then I still advect damage with the flow, and damage would then still continue to feed back with the viscosity of the ice. And this is a fairly simple scheme to implement in an ice sheet model. That's an advantage of working in a fully viscous framework here, is all the big ice sheet models are primarily fully viscous. So we'd like something that we could run in those to account for fractures in a sort of in a numerical scheme that's not too complex or too costly. And so with this Larsen B work, I was able to sort of put some bounds on what these, at least for that ice shelf, what these parameters should be. In principle, those shouldn't vary too widely across ice shelves, but I haven't been able to assemble a good time series for another ice shelf to check that. Okay, so what I could do then is I can then make some forward model predictions using this framework. In this case, this is actually forcing the model with the observed velocity trend just to see if, in that case, it reproduces the observed damage. And through time, it actually does quite a decent job. Now, one thing that's clear is that I need some probably level set scheme for taking care of fracturing, especially when I have a big rift form. This rift ultimately did tear off a tabular iceberg here. So rather than representing that by some growing band of damage, it would make more sense to have some scheme for chopping that ice off. But that's work in progress. So the next stage of sort of testing the model is I wanted to compare the influence of damaging against some other sort of baseline model experiments. So there are a number of model intercomparison exercises that the ice sheet modeling community uses. The one that I chose to implement this damage framework in is this MISMIP Plus, which is a kind of idealized marine ice sheet experiment. So if you think of that sort of cross-sectional marine ice sheet example I talked about earlier, if I sort of extrude that in 2 dimensions and then put a deep central bedrock trough in it so I get some laterally convergent flow, that's the sort of shape of the bedrock. So I've got bedrock that points downward toward the interior of the continent and a trough in the middle, so I'm getting some convergent flow. Then there are a number of, the details are maybe not so important about the rest of the model setup, but I've implemented this damage framework in this ice sheet system model, which is this sort of NASA, JPL, UCI, UC Irvine model. We use, and I maybe didn't stress this earlier, but pretty much always when we're modeling ice shelves, we're working with depth integrated set of equations because we don't have any vertical variation in velocity or at least it's negligible in an ice shelf because there's no basal shear stress. So we can work in 2D, which is nice. I've got a subgrid parameterization for allowing the grounding line to migrate. And here I'm going to show results for sort of nominal 500 meter mesh resolution. So in cross section, here's the sort of ice sheet we spin up to a steady state. It's a little hard to see, but it is stabilized initially on reverse sloping bedrock. And that's because of this central trough. So then in plan view, looking down at the top, I haven't allowed any damaging in the spin up, so there's no damage here. And the grounding line position is specified by the change in color at the bottom panel. And there's these sort of wings of the grounding line associated with that trough. It's kind of a funny feature, but those are robust. So if I start from a steady state and then sort of turn on this damage evolution model. First, at steady state, the stresses in the shear margins are very high, so it's sort of reasonable to expect that this is where we would expect fractures. And indeed, as soon as I start running, this is where we see damaging. And the grounding line starts to move. It doesn't move real fast, but if I run here for, say, 100 years, I get some movement of the grounding line. I don't show the velocities, but the velocities increase because there's less resistance in the shear margins. And I've limited, in this case, the damage to not go over 0.5. The reason is that, for that, is that in this particular model scenario, it was set up to sort of not accommodate really any weakening beyond that, because if I allow damage to go any higher, the ice shelf sort of collapses within a few years. So it was designed to be an experiment to really sort of whack away at an ice sheet and see how rapidly you could get it to move by melting it from beneath with an ocean model. It wasn't really designed to look at this kind of weakening. So to actually get something that looks reasonable through time, I have to not let it damage too much, but just to demonstrate the principle. So if I then turn damage off, I still have this weakened ice in my system that I have to advect out of the system. So the influence of that fracturing and weakening is still carried by the system. Even if I'm not producing new damage, it takes a while to advect it out of the system and recover. So for comparison, the sort of melting perturbation that is used, or one of the melting perturbations that's used in this experiment, is just a parameterization that specifies a basal melting rate as a function of the draft of the ice shelf. So here, strong yellow colors are the melting rate. And if I turn that on from the steady state position and just chop away at the bottom of the ice shelf, I can really get the ice sheet to retreat. So if I look at something like the ice sheet volume change in this set of experiments, the green now is where is this melting parameterization. I can really eat away at an ice sheet by melting it from below. But if I turn that perturbation off, the ice volume immediately begins to rebound. So if I get cyclic variations in ocean melting at the base of an ice shelf, you can get recovery right away. This moderate damage simulation, I don't get the same magnitude of change, but if I turn that perturbation off, I continue to lose ice for several hundred more years because I've still got that weakened ice in the system. I've got that history of fracturing still affecting my ice sheet. You can look at, we often in the modeling community look at the ice volume above flotation rather than the total ice volume in these experiments because that represents the potential sea level contribution to the ice sheet. And that, in the melting perturbation, that continues to decrease after the perturbation is turned off. Same with the damage simulation. If I combine the two, and this is the most realistic scenario, if I melt away at the bottom of an ice shelf, I should expect that the stresses in the shear margins will increase, so I should expect that there will be a feedback between melting and weakening of the shear margins. So if I turn on both of these perturbations, indeed that's what I get. I get a strong thinning signal from the melting, and I get damaging that within just a few years comes all the way across the grounding line. And then essentially the ice sheet starts to, the ice sheet really starts to run away, and it becomes a question of how realistic or how how far to run a simulation like this before you should really say the ice shelf probably collapses and you should remove it. But if I say, just for the purpose of illustration, run this for just 25 years, the typical perturbation length is 100 years, I get a drastic decrease in ice volume, and then it continues to lose volume for several hundred years. And for the ice volume above flotation, I continue to lose volume from my ice sheet for, again, several hundred, in this case, 100 and some years after I turn off the perturbation. Okay, so that was kind of the end of what I wanted to get through. So we can kind of summarize that we can infer damage from assimilating remote sensing observations in an ice sheet model. Fully viscous damage models, like I showed here, can be pretty easily implemented in large-scale ice sheet models for making predictions of future ice sheet evolution. These things seem to handle shear margin evolution pretty well. That's clearly important for ice shelf buttressing. It's probably a good framework for looking at iceberg calving. There's been a little bit of work on damage-based calving models. A fully elastic damage model may be more appropriate for things like rifts and for things like tabular calving associated with rifts. I think ultimately we're going to need to move toward fully viscoelastic models to handle a lot of this stuff, but the ice sheet modeling community is, going to continue to work in fully viscous models. So the better parameterizations we can give them to work within their viscous frameworks, the better off they're going to be. The damage carries a history of fracturing. That's important. We haven't really addressed healing much, and that's on the to-do list. That's all I have. Thank you for your attention, and left some time for questions.
Just a second, I need to apologize because John asked me to share this session, but then embarrassingly I was late. So sorry about that. But my name is Jukka Tuhkuri, I'm from Aalto University, Finland, and I will be chairing this afternoon if I'm not late. Okay.
Concerning the suture zone that you have shown that are arresting the rift,
Yeah.
are these suture zones creeping faster? I mean, in other words, are the ice is damaged along this zone or not?
There's in the velocity data, appears to be no differential shearing for the most part in these zones. So they're moving along at the same rate. And we see on both sides, in many of these suture zones, we see fractures coming right up to the boundary of the suture zones, but the suture zones themselves don't look that damaged.
Okay, so it's because if it would be highly damaged, you could explain that it would just blunt
Yeah.
the crack tip.
Well, I think that actually is probably what's happening, because these zones are much more heterogeneous. So you've got former shear margins of neighboring glaciers. These shear margins are quite damaged and fractured to begin with. They come together, and even if they heal, there's a lot of pre-existing planes of weakness there that may give rise to preferential or more blunted fracturing, more distributed fracturing than you get in meteoric ice.
Okay, but it's not measurable, I mean, in terms of your damage parameter.
Not from an inversion, because it doesn't lead to an enhancement in strain rates. But that's something that we have proposed to measure in the field and would like to figure out how to measure in the field, because that's the sort of hypothesis.
I thought it was very interesting. I like the idea of how the damage model can actually model the whole of the ice shelf history. But just in terms of the collapse, have I correctly understood that actually it wouldn't sort of predict that sudden catastrophic collapse, so you have to have something else in the model to do that? Is that correct?
Yeah, ultimate collapse is probably not something that you're going to handle with this kind of model. I mean, I think if we expect on the Antarctic Peninsula, if we expect more collapses like we saw with Larsen B with increased surface melting and surface melt ponding, then if we had some model or mechanism for accounting for surface water and surface hydrology, we might be able to parameterize that and potentially predict something like a collapse. But yeah, but I wouldn't expect to model the actual collapse.
Two questions. So the suture zones are, I believe, are regions of quite a lot of marine ice. Right?
Yes.
So is there any empirical evidence to suggest the mechanical properties of marine ice is substantially different from that of the surrounding ice? Because the salt content is very low in the marine ice. So that's the first question. Is there any evidence?
So I believe there may be some proxy evidence from seismic data, active seismics, or even or radar data. I'm not the one to answer that.
And we did experiments both on meteoric ice and on marine ice, measuring effective toughness, so that data is available. But I think the issue about the marine ice and the suture zone is actually its temperature. It's very different. It's very much warmer, isn't it?
It's very much warmer, yeah.
Really? Because it's been there for hundreds of years, and temperature there is a diffusion equation, and temperature does diffuse, and it does take hundreds of years. So that seems half strange to me. But anyway, on to the second question, since I don't believe the answer. You kicked off your talk by talking about the West Antarctic ice sheet instability.
Yeah.
Okay. So I'm quite interested to see what, including this damage model in this viscous ice sheet models, what impact that will have on whether this West Antarctic ice sheet instability emerges from these simulations. Any comments on that?
Well, the models that don't use damage predict that this sort of instability is underway. Damage is really only going to accelerate that. So it's really a matter of timescales. I mean, I think that's the important question now: is what is the timescale of this likely inevitable collapse?
And you mentioned it was stuck. This was put into the MISMIP, right?
Yeah.
Is it going to make its way into the next CMIP set of experiments?
So the damage stuff didn't go into the standard MISMIP intercomparison stuff. So I'm writing that up separately.
Okay.
Not sure where that will.
So no, but in the next next generation of flight models, it may be included.
But yeah, potentially.
So I was involved in a project on the McMurdo ice sheet,
Yeah.
where the runways are, and there the ice sheet is totally saturated with brine. Is that an issue that you have to worry about?
So this is something that's come up. This saturation of the firn before you get to the close-off depth and glacier ice formation. Actually, that there are areas that may become saturated with brine. I don't know what kind of influence that will have. I don't have a good answer for that, but it's sort of on the radar as a process that may be worth considering.
So in the damage inversions that you did,
Yeah.
it seemed like the damage parameter was taking up anything that couldn't be explained by variations in the B parameter through temperature.
Yeah.
Okay. Do you have a way of ground truthing or knowing whether the predictions that you make are relevant to the actual measures?
It's a good question. I mean, we've done some sort of basic spot checking by looking at just satellite imagery to see that we get damage in places where we see fractures. That's the sort of most obvious one. But there are a lot of places where you see fractures, but you don't infer damage. And I'm not sure you should infer damage because you've got many fractures that formed somewhere far upstream under different stress conditions, and now have been advected down to different stress conditions, and they're not representative of the local stress anymore. They're sort of being fractures that are sort of being carried passively along. So I shouldn't expect to invert for those kinds of fractures because they're not sort of locally enhancing the flow. But aside from that, yeah, you're right. I mean, with these inversions, we're sort of lumping everything we don't know into one parameter. So there's a number of things that get mixed up there that are tough to partition.
I had a couple of points actually. One was an answer to Danny, which is that there are observations of marine ice, and it is considerably warmer than the meteoric ice that's around it. The other one was following on from that last question, which was
You can talk about to me about that later, actually.
I'll send you some paper. The other one was following from that last question, where it seems to me you need an anisotropic damage model, because that ice you were talking about won't be shearing when you're observing it, but it is still weak in a different direction, if you see what I mean. So I was wondering what you thought you were missing from it being isotropic.
Well, yeah, so I mean, you start with an isotropic model, but clearly fractures by nature are anisotropic. They have a direction, and so they should influence the ice differently depending on how you load with respect to the orientation of the fracture. So it would be desirable to have an anisotropic damage model. That's considerably more complex computationally, but that is a target.
Doesn't that depend on whether you resolve the anisotropy or not? I mean, if you have an isotropic model ran at sufficiently high resolution, you can have a crack and it can affect the stress balance. There's no need to necessarily have a subgrid scale anisotropic model. I mean, it depends on whether you talk about the anisotropy at the crystal structure level or the level of there being macroscopic cracks.
Yeah, more at the level of there being cracks. Yeah, I suppose in principle, you could run something that just was highly enough resolved to see individual cracks, even if you were treating them isotropically.
I'll take your relationship damage to strain rate.
Mm-hmm.
Your parameters, the upper level of stress you can have.
Yeah.
And the decay. Does that mean there should be a strain rate we should never see on an intact ice shelf because it would be d equals 1, or is there a or d equals 0.6?
Well, I mean, it's sort of
heuristic calving law.
asymptotically damage, sort of asymptotically approaches 1. So
The restraint rate, it would reach you on 0.6 or... It's just curious that there hasn't been a successful calving law based on, just the strain rate as observed from...
yeah.
So I wonder if there are, what could be missing, why that law hadn't already emerged as a function of strain rate if it was sort of so easily mapped onto strain rate.
Yeah, that's a good question. That's a good, tough question. Yeah, people people have looked actually hard for these strain rate relationships to explain calving. But I guess that's yeah. There must be something about having the history there as well, because the damage is feeding back with the strain rates. The short answer.
Short one, short one.
Yeah.
We have
Isn't that the sort of thing that we were talking about before? I mean, the overall strength just doesn't depend upon the stress or the stress derived from the strain rate. It also depends upon the crack length as well.
Yeah.
So you have to always have those two factors together. So the strain rate in itself would not be the answer just as we saw before lunch.
Okay, thank you very much.
Thank you.